Hi, my name is Oldridge. I'm from NVIDIA, and I'm here to present my talk on recommender systems at scale on the GPU. My team at NVIDIA, the Merlin team, has been working on developing tools for accelerating recommender systems for both the ETL phases as well as training and inference. And I'm excited to share some of the advancements and developments that have happened in the GPU space around recommender systems to allow us to get to the level of scale for these larger models. So one of the things that I want to highlight and share, because not everybody is aware of the RecSys spaces deeply, is that recommender system models are not the same as computer vision or NLP models. So if you look at the classic computer vision models, you're feeding in an image, which is a fairly large piece of data, and then that image gets passed to the model, and the model is taking up the bulk of the weights on the GPU. So the GPU space is taken up by that broader, larger model. In the context of NLP, you've got this concept of word embeddings. And so the embeddings are these sort of vector representations of words that allow you to provide a vocabulary for the model to learn the context of those words in that setting. But those vocabularies are typically around 30,000, and they're, again, fairly small relative to the size of the model. The models like the latest transformer models, like Megatron or BERT Large or GPT or XLNet, they're all quite large, and you can distribute the model part itself across multiple GPUs. But when it comes to recommender systems, the bulk of the recommender system model is actually made up of those embedding representations. So for NLP, the embedding representations were representations of the words, and we're training a model to learn how to understand those words in context. In the RecSys space, the embedding representations are representing the user or the item, and that can be, in a retail environment or in a social networking environment, can be millions or hundreds of millions of users or items, right? Potentially into the billions. And so, the amount of memory and the amount of storage needed has made it traditionally very, very challenging to do those types of models on the GPU. Right. And part of this is a little bit exacerbated by the fact that a lot of the deep learning tools that were being developed over the last decade, they've been developed during the rise of computer vision. Computer vision has been the main sort of dominant player at the beginning of the development of deep learning. And so what I'm going to walk through today a little bit is sort of some of these RecSys models and how we can kind of take the different pattern of access and the different requirements in the RecSys space and develop both the software, as well as talk about some of the changes that have happened on the hardware side to help demonstrate how we're able to get to scale on the GPU very easily now. And it's an exciting new time for the recommender system space. When I first got into doing recommenders or deep learning based recommender systems, 5-6 years ago, what I found was that out of the box performance of RecSys models on the GPU was poor. And I think, we've done a number of things since then to accelerate that. And I'm really excited with some recent developments on the TensorFlow side. We've made some massive improvements there. But what we found was both the hardware side, like it was very hard to fit all of the embeddings for those users and items onto the model. And as well, like the way that data is loaded on, and I'll talk about some of these other aspects, there was just this impact in performance. And you could see like a 4 to 5x perf difference on previous generation hardware, but that generally wasn't enough to justify the cost of migrating your pipelines over from CPU to GPU. And so as a result, a lot of people, even today, do recommender systems on the CPU. But what we're seeing is that, in the last couple years, hardware has really come a long way, right? And that stemmed partly from this recognition within NVIDIA that we need to make improvements, that one of our gaps is this memory performance, right? And so, in these two graphs show over the last 5-6 years, the transformation from GPUs having, 6 and then 12 and maybe 16 gigs of memory up to today's A100 model or GPUs that have 80 gigs of memory. And it's not just about the actual amount of memory that you have on the GPU. Really, like, one of the most important components is the memory bandwidth as well. So when the majority of your model is made up of these embeddings, really how fast you can get data off of those embeddings becomes increasingly important. And so that's something that's been improving as well. And what we're seeing is, we're up to roughly 2 terabytes of memory bandwidth on an A100 GPU. And that makes a massive difference when you structure the memory accesses correctly. You can get incredible performance of the GPU for recommender system context. And that 2 terabytes per second is, it's an order of magnitude faster than you see CPU memory access. And so not only is the compute faster, but the memory access is much faster on the GPU as well. And that makes a big difference when it comes to performance. So you can see this sort of the scale on a single GPU, but one of the other things that's been evolving is, NVIDIA no longer thinks of itself as a GPU company, but as a data center company. And we're really thinking about how do we scale these systems, to connect multiple GPUs into a much larger ecosystem. So, the DGX A100 is our sort of our flagship. Like this is a combination of 8 A100 GPUs, and so you get 640 gigs of GPU memory with very fast interconnect between them. So you're looking at 4.2 terabytes per second of interconnect between all the GPUs, and that really helps you scale recommender system models and grow to the point where these models that were unheard of are now absolutely accessible on the GPU. And I think that growth happens both at the DGX A100 level, and also you can combine multiple DGX A100s into a superpod, and really like that interconnect is allowing us to scale way beyond what you could even begin to imagine 4 or 5 years ago on the GPU, right? And part of the story here is that data availability for the recommender system space is the key to better performance, right? And so when you look at the performance when you're going from storage or a RAID, you're talking about gigabytes per second, maybe tens of gigabytes per second. From CPU memory to GPU memory, you get about 10 gigabytes a second. But from GPU memory to the GPU cores, you're looking at hundreds or hundreds of gigabytes or terabytes per second. And that that getting that right data onto the GPU memory and making sure it's available for the GPU processor cores is a critical part of what we do. And so that on the software side is a large portion of what we've been working on. So the biggest challenge or question that I've had over the years, and certainly 3 or 4 years ago when I first set out at NVIDIA to do this, is these huge data sets require huge embeddings, and my model just doesn't fit on the GPU. So it doesn't make sense for me to use GPUs, really, does it? And I think like what I'm going to introduce is today is some techniques that allow us to extend. First of all, you can extend in the hardware space, and you get significant advantages from doing so. But even in the software space, you can use sort of some caching techniques to really accelerate the performance of your RecSys models on GPU without requiring you to scale across the entire GPU cluster just to get access to the memory. And part of why we're able to do this is, items and users, they follow a power law distribution. So you can see, like a very small percentage of the users, a very small percentage of the items, those are the ones that are being frequently accessed across most of these data sets. And that allows us to, develop caching strategies and think about what data do we need where, and putting that, the most frequently used data right in that GPU memory so that it's readily accessible, and the less frequently used data, in other places. You can see users kind of follow that same distribution, and it makes sense. That's an access pattern that's very common in the world, and so what we're doing is developing software today that takes advantage of that. So I'm going to share sort of 3 examples of how we're taking advantage of that, or leveraging those principles of data availability and thinking about where the data lives and how we can get the GPU cores better fed, and just share how we see these accelerations happening. So the 3 examples I'll cover today are data loading of tabular, and by tabular I really mean RecSys data, or recommender systems data, model oversubscription, or another way of thinking about that is sort of caching the embeddings during training, And then, one of the technologies that we're really working on recently, and I'm excited to share, is a GPU embedding cache and parameter server technology that we've been working on in order to do caching of those at inference time to be able to serve much larger models on a smaller GPU. So on the data loading side, this was sort of my starting point at NVIDIA. I spent a lot of time working on this project as an individual contributor before sort of growing the team and taking over as manager on the Merlin side of things. And so it's very near and dear to my heart. And the core idea here is just like, when you look at the access patterns of how data is accessed, it was developed during the era of computer vision. And so the idea behind most data loaders, if you look at the sort of the base data loaders in the core frameworks, is that you start by creating this random index of data points that you're going to access. And when that data is an image, that's maybe okay. I mean, there's certainly better ways of doing it, even in the context of images. But for recommender systems, that's an incredibly painful way to access the data, because what you're doing is sort of grabbing this random data, and the data itself is quite small. There's very small subsets or very small item level data, and you've got to grab thousands of them or tens of thousands of them to pack them into batches. If you do all of that and the data set doesn't fit in CPU memory, then what ends up happening is you're actually creating this random access pattern to the GPU, or sorry, to the disk, and that's just about the worst possible access pattern you can. So in this world of computer vision, data loading works by randomly shuffling the data, collating that data into batches, moving each batch to the GPU, and that data access pattern is of randomly grabbing single items is just not feasible in the RecSys space with billions of examples, and especially when that data set doesn't fit into host memory. So we sort of restructured and thought, well, what if we move large chunks of sort of pre-shuffled data to the GPU, shuffle that again locally on the GPU for a final extra randomization, and then from that in-memory chunk on the GPU, access and pull batches into the traditional framework. So we're basically redesigning the data loader for a large number of small items instead of the original design, which is for a small number of large items. And by doing that, what we're saying is, okay, we're gonna take advantage of the GPU fast interconnect. It's very fast to transfer data to the GPU if you do it in large batches, right? And so the larger the batch, the more effective you are at these kinds of data transfers. And this has allowed for a massive improvement in performance. So one part of what motivated us to do this is and this is sort of a comparison that we've done on both TensorFlow and PyTorch. This is the chart for TensorFlow. Is in those gray boxes, what you see is sort of the throughput in samples per second of the model. And one of the things that we did to test and validate, and this is something you can do yourself very easily in your own models to see, do I have a data loader problem, is you just turn the model into a no-op. You basically have it always output one. So you pass the data in and then you output one. And so there's no compute happening. The model is only doing the data loading portion, and then it's iterating through that. And what we found was that when we switched the training over to only data loading, the performance was exactly the same in TensorFlow. And that told us, okay, there's the bottleneck here on the TensorFlow side and on the PyTorch side on these traditional data loaders is in the data loading. And so we created this NV tabular data loader and tested this new data loading strategy. And what we found was we could get that throughput if we were only doing data loading up by 24 times. So we were able to data load orders of magnitude faster, right? Now you don't get that full advantage in terms of the final performance, because obviously the models are going to take up some of the time, but that's what you want taking up the time when you're doing training like this, right? So we accelerated on the training side, both with sort of traditional and then with mixed precision with AMP, and what we found was roughly an 8 or 9x performance difference. So you can speed up your training significantly if you just get the data to the GPU and then leverage the GPU in that context. And that sort of that transferring of data in large chunks is a large part of what we've thought about in terms of how do we improve the performance of recommender systems on the GPU at scale. Obviously we want to make sure that the performance is exactly the same. So we've tested, the convergence behaviors of all of these, and and validated that it's exactly the same. And we see identical performance between these methodologies, right? So, it's an important part of what we're doing is making sure that these systems that we're developing, we're not exactly following the same traditional method of the data loader where we're fully randomly sampling. So we need to validate that that's a reasonable thing to do. And it turns out that it's perfectly fine. And you see, exactly the same convergences. I said I'd share 3 things, but there's a little bonus in here. RecSys data formats are, traditionally, like it's tabular data. It's these rows and columns of data. If you have a raw data set in CSV format, uncompressed, you're looking at a very large format. Most people would not store tabular data in that fashion, certainly not at scale. It turns out that if you take that CSV and you transform it into a TF record, like for the base TF record style, the data actually gets bigger. So you end up with this much larger data set. There are ways to pack it into batches, but that's a very lengthy process and something that that we're trying to help the TensorFlow team optimize, because it turns out that makes a huge difference in performance if you sort of pre-pack your batches, similar to what we're doing on the GPU. But to highlight what it is that we're doing, we store our data in Parquet format. It's a column-oriented compressed format. It's supported by lots of other frameworks, including Spark. You can access the data, you can view it, you can take a look at your data after the fact, and that's one of the big advantages. Is you can store 4 to 5 times more data in Parquet files. So and the advantages there also is that you're cutting down on I/O, right? Like it's not just that it takes less storage, but you're transferring less data over because the decompress of the Parquet is happening on the GPU side. So there's a lot of advantages to using Parquet. So just to summarize at a high level, the data loaders we've developed, we were able to speed up TensorFlow and PyTorch pipelines and recommender systems by 9x. You were streaming data sets in big chunks rather than item by item, right? And the thing, the other challenge you run into with sort of more traditional data loaders is typically that those data sets have to fit in host memory. We don't have that requirements on our data loader side. So you can scale up to these terabyte, petabyte scale data sets with NVTabular, which is pretty exciting. We're focused on integration, so you can definitely you can work within TensorFlow or PyTorch, and the data, like the APIs look nearly identical, right? You use our Keras sequence loader and specify the engine being Parquet, and essentially you get the exact same functionality using these calls. You're using traditional Keras calls. You're using the traditional .fits. We're just leveraging our data loaders to help accelerate the process to make sure that the data feeds into the GPU in an efficient way. So that was the first. This next stage is sort of how we can use kind of similar principles of getting data onto the GPU, but in this case, sort of getting around the memory limits by using embedding caches for training, right? So, we talked about this earlier. Huge data sets mean huge embedding tables. So if you can't fit those embedding tables on the GPU, then you have a choice. You either put them on the CPU and then transfer them over, and you have I/O issues, then it's much more challenging to develop your model, or much slower when you're training your models. Or you scale your cluster to encompass all of those, and that's generally not cost effective, although in many cases it can be if you're, if you're dealing with really, really huge models. Scaling to multi-GPU and multi-node is something that, that we support, obviously. We even have a custom framework called HugeCTR that's part of the Merlin project that helps with that scaling and helps do things like distributing the the embeddings across multiple GPUs and multiple nodes, and really helps, in the performance side of things. But if you can't sort of scale across even those multiple GPUs and multiple nodes, if the model still doesn't fit, there are strategies and techniques you can take advantage of. So we've talked about the power law distributions here. This technique we call internally model oversubscription. The idea is just essentially to split the training data set into chunks, to partition it into multiple blocks, and then load the embeddings for each block independently in those big movements to the GPU like we talked about. So we move the embedding partitions for that subset of the data to the GPU, train on that subset of the data for the first portion of the training of that epoch, and then transfer those embeddings back off and transfer the next set on. And so that looks something like this. You can train terabyte scale models on a single GPU. You're limited in the sense that you need to be able to fit those subsets on the GPU. But we saw those power law distributions really, like, there's a very small subset that are pretty much always going to be there because they're constantly being updated, and there's another subset that are part of the long tail. And so essentially what we're doing is swapping out that long tail in terms of the embedding tables. So each portion of the data set is going to be trained in sequence. It's still effectively the exact same training cycle, but what we're doing is just hot swapping in and out in terms of the cache that's storing the embedding. So we're making sure that the embeddings that you need are on the embedding tables before that sequence of the training, right? And that allows us to really effectively scale the amount of memory available to store on the embedding tables to well beyond the GPU memory, even beyond the CPU memory. We can store some of that in not just host memory, but actually in physical storage as well. And it turns out you can take that same principle of the GPU embedding cache and apply it at inference time as well. So the inference serving of models with larger GPU memory, if you train a really massive model, and you're training this on a DGX A100 or a SuperPod, you've got embedding tables in these much larger spaces. Really, like the challenges are the same, but you don't know exactly what embeddings are going to be on the GPU at that time. So we've still got these same huge embedding tables that we need to fit on the GPU, but we can't take advantage of the fact that, like, during training, we can kind of pre-compute and figure out, okay, for this quarter or this subset of the data, these are the embeddings that we need to have on there. So what we need is a more active caching mechanism, right? And again, we're leveraging this high bandwidth memory. We're really taking advantage so that the embeddings that are used most frequently are sitting already on the GPU, and we can get them to the GPU processor cores incredibly quickly. And we only go off GPU for the larger vocabulary. So we can grow the embeddings and take advantage of those same power law distributions. The caches are designed exactly for that type of memory access, right? And so the embedding cache on GPU is just this idea that you can deploy models to production for inference. You can have multiple instances of the model sharing the same embedding cache, and you can store those frequently used embedding representations on the GPU itself. And when you have a cache miss, then you go to the parameter server and you pull the data across. But you're not pulling the entirety of all of your embeddings across, and so it's the amount of I/O is much lower. It's much more efficient than having everything off, and it doesn't require the scale of GPU of having everything on, right? And so we've got this hierarchical caching of some of the embeddings are sitting in GPU memory, some of these embeddings are sitting in host memory, some of these embeddings can even be sitting on disk, as mentioned, right? And on the back end of that is this idea of a shared parameter server that is able to provide that request when you miss the cache. So when you do the embedding lookup on the models and you miss the cache, then you go back to the parameter server and pull and grab the data. And what we're doing right now on the Merlin team is taking this code, which is part of that huge CTR framework that I talked about. And huge CTR is a custom C++ framework. It's incredibly fast, incredibly efficient. But a lot of people, they have an existing TensorFlow deployment. They have a system that's already running. They want to be able to leverage that. And so what we're working on right now is how do we migrate this code over from this custom framework into TensorFlow to provide access to it for everyone. And this is something that's that's coming out very soon. So the highlights of the story, really, the hardware today is radically different. We've seen this incredible growth in GPU memory and in GPU bandwidth, and that means that that old story of there's not enough memory on the GPU to fit the compute, or sorry, to fit the recommender system models, and the ratio of memory to compute is imbalanced for recommender models is no longer true. With the newer hardware, we're really seeing this revolution in terms of what's possible or capable on the GPU. It's super exciting, and not just on the amount of memory, but memory bandwidth has also increased exponentially, and that makes a huge difference. When most of your model is these are these embeddings, it's really important that that ratio or that performance of your memory bandwidth can make a huge difference. Similarly, we've begun to recognize this challenge of recommender systems are not the same as computer vision models, and so we need to think about them differently. But the really cool thing is that that a lot of these improvements are happening. They're unique to the RecSys space, and we're able to take advantage and do some amazing things in RecSys that you can't do in computer vision because the concepts aren't applicable. And so I'm really excited by the direction this is taking. I think there's a huge revolution that's going to happen over the next 4 or 5 years in terms of what's possible and available on the GPU, and I'm excited to be at the forefront of this. I manage a team called the NVIDIA Merlin team, and our whole kind of core ideology is providing easy to develop, performant end-to-end recommender systems. On the GPU is actually not entirely true anymore. We're now developing software for both GPU and CPU, and I think that's an important addition and change to our mandate. We're really starting to think about on the team, how do we support the broader ecosystem of people developing recommender systems in general, and and helping people start with simple, more straightforward traditional recommender system models on the GPU or on the CPU rather, and then begin to scale on the recommender system journey from those models to more complex and powerful recommender system models on the GPU, like deep learning. You can check us out on GitHub. All of the tools and technologies I've been talking about are open sourced. So we have github.com/NVIDIA-Merlin. We also have a Medium blog if you search for NVIDIA Merlin. My name's Even Oldridge. You can send me an email at eoldridge@nvidia.com or hit me up on Twitter, even_Oldridge. I'm passionate about recommender systems and embedding spaces and acceleration here, and especially developing these systems at scale. And I'm very excited to talk to anybody who wants to share their thoughts or ideas in the space. So thank you very much.